Okay guys, in this video segment we're going to cover our last type of concentration, which is molality, and then move on to colligative properties and how colligative properties affect solutions. So far we've talked about molarity, percent by composition, parts per million, parts per billion. We'll get into some other concentrations in the acid-base unit. What we haven't done yet is molality. Okay, it sounds a lot like molarity, but it is a different thing. Okay, so molarity, molality, very similar words, but you got to be able to keep those two things separate. Now with molality, we don't use this type of concentration very often in the world of chemistry because we're dealing with kilograms of a solvent, which most of the time we like to use volumes when we do solutions because most solutions are based off of water. Now, however, there are certain cases where molarity doesn't work. Okay, molarity doesn't work whenever you have a temperature change through your experiment. And with molarity, because you're doing the volume of a solution, as temperature changes, the density of that solution will change, thus the volume would change. So if you actually change your temperature through an experiment, the actual molarity would be changing with that temperature. So it would be temperature dependent. Now molality is not temperature dependent. What we mean by that is that at any temperature or any change in temperature, it would be the same value. So we really use it anytime we talk about something called colligative properties, which we're going to go into in our next slide. Molality is symbolized by italicized lowercase m. We use lots of m's in science and chemistry, so just kind of keep track of them. Molarity, remember, was a capital M, so this is italicized lowercase m. If you're handwriting it, just write like a normal lowercase m, but just make it kind of fancy. And when we calculate molality, it's moles of solute divided by kilograms of solvent. Okay, so we're not dealing with solution anymore. It's moles of solute versus kilograms of solvent. So we can keep track of both the solute and the solvent in our molalities. Okay, we're going to do a quick practice problem just to make sure that we're comfortable with molality and make sure that we can actually solve and calculate things with molality. So here's our practice problem. How many grams of benzene must be dissolved in 500 grams of acetone to make a 1.25 molal solution? Okay, so go ahead and pause the video now. Try the practice problem using that equation and a little stoichiometry, and then we'll come back and I'll do the example for you. Okay, so our practice problem gives us 500 grams of acetone, so we know that's our starting point because that's a number that is a single label to it. And it also tells us that we have a 1.25 molal solution. So a 1.25 molal solution means it's 1.25 moles per every 1 kilogram of solvent. So that's what that's telling us. Now, acetone is our solvent in this process. So this kilograms of solvent is kilograms of acetone. So we can use this to help us get from grams to moles. Now, 500 grams, we know that there's 1,000 grams for every 1 kilogram. And we know now from this we can put into here, for every 1 kilogram we have 1.25 moles. And then this is moles of solute. So the solute in this case is benzene. Okay. So we don't really need a mole ratio because we went from solvent to solute within this process right here. So we go from 1.25 moles, and then we can say for every 1 mole of benzene, we get its molar mass, which happens to be 78.12 grams of benzene. Okay? So again, molality, molarity, they're concentrations, they're ratios, so they can be used in our stoichiometry. Okay? We have our grams, we converted from grams to kilograms, kilograms to moles, and then moles back to grams, because we can make that switch between our solvent, the acetone, and our solute, benzene, with this step right here. Okay? So if we do that, and we come back to the slide now, we see that here's our problem, and we get 48.8 grams of benzene. Okay? So that's molality.